Scientific inquiry and understanding is derived almost entirely from making observations. Although this empirical nature of science has been recognized since the time of Galileo in the early 1600s, the scientific method was developed as a formal construct only since the mid-1800s. Not all scientific studies follow this method rigorously, but most adhere to the basic principles and methods. The method almost always begins with an observation, perhaps a property of nature, or possibly a measurement that gave an unanticipated result. Surely many children have wondered at some time, why is the sky blue? The next step in this formal process is to pose a conjecture or a hypothesis to explain the observation. In this case, we might suppose that one of the components of air absorbs red light, letting the blue light come through to our eyes. We then would set out to design an experiment to test the hypothesis, perhaps by measuring the absorption coefficient of air. Note that the experiment cannot prove the hypothesis correct, because there may be more than one explanation that's consistent with the experiment. Instead, experiments are designed to falsify or invalidate the hypothesis. The experiment in this case shows conclusively that the absorption of red light by air cannot account for the fact that our sky is blue. So our hypothesis is wrong, and we must go back to the drawing board to find a new and better hypothesis. This time we conjecture that dust particles in the air might scatter light, and that blue light is scattered more efficiently than red light. So we design an experiment to measure the wavelength dependence of light scattering by small dust particles, and it turns out that the results are consistent with our hypothesis. More detailed experiments show that when we look at the sky at angles far away from the sun, some of the blue light is scattered by dust particles in our direction so we can see it, while most of the red light passes through the atmosphere away from us unseen. The process of refining the hypothesis and conducting more and more detailed experiments continues, and the hypothesis gradually evolves into a theory, which not only predicts the outcomes of experiments, but also provides an underlying explanation of why the process occurs the way it does. In this case, Rayleigh theory also explains why sunsets and sunrises are reddish-orange. It's because when we look at regions of the sky near the sun, light scattering over long distances through the atmosphere scatters blue light away, letting longer wavelength orange and red photons reach our eyes. This continuous cycle of improvement between observation, hypothesis, and experiment is the way that most scientific research is conducted. Incidentally, the term theory is sometimes used in the popular press in the context of a conjecture or hypothesis. However, scientists use this term to denote a well-established model that not only predicts the observations, but also provides a detailed underlying explanation for them. A theory answers the what and the why. I'm Chuck White. I'll see you again soon.